Welcome to the presentation on our work on combining core-guided search with cutting planes reasoning. My name is Jo de Vriend, and this is joint work with Stefan Gocht, Emir Demirovic, Jakob Nordström, and Peter Stuckey. Suppose you are solving an optimization problem. There is an objective to minimize and a set of solutions for which you want to find the best one. Core-guided optimization instructs a combinatorial solver to find a solution at the absolute lower bound of the objective function. If no such solution exists, it will increase the lower bound based on the answer of the solver, and it will try to find an optimal solution at this new lower bound. This process repeats until the solver finds a solution at the current lower bound, which is then optimal. Before we dive into the details, let's first denote the context in which we work. We assume all the variables of the problem are 0 or 1. The constraints of the problem are linear inequalities, which together form a formula phi. Sometimes we will refer to a negated variable, which is simply 1 minus the variable. Literal then is a variable or its negation. Finally, the objective O is a linear function to be minimized, for which we assume, without loss of generality, that it only has positive coefficients. Basically, we are working in a context of 0-1 integer linear programming. The solvers we use take as input just the formula phi and a set of literals alpha, which forms the assumptions under which we want to know whether phi is satisfiable or not. As output, the solver should either give a solution satisfying both the formula and the assumptions, or a constraint implied by the formula which is falsified under the assumptions. Alright, how does classic core-guided optimization work? Summarized, it's a loop with four parts. First, a solver is called to solve the formula with a carefully chosen set of assumptions. Assuming this to be unsatisfiable, a core constraint is extracted. By analyzing this core, the problem is then reformulated, and the lower bound for the objective function is derived. After this, the loop closes by calling the solver again on the reformulated problem. The loop stops when the solver returns a solution, as in this case, the solution should be optimal. The original core-guided work stems from the maximum satisfiability or MAXSAT domain, but it has been successfully applied to answer set programming and constraint programming as well. The example I'm about to present is based on the OLL and 1 method from MAXSAT and ASP. Suppose you have some unspecified formula phi and a simple objective function. The first step in the loop is to call a solver with a set of assumptions. The assumptions are chosen so that the objective value is minimal. As we only have positive coefficients in our objective, we assume all variables to be false for an objective value of 0. The solver now reports that no solution with 0 objective exists. Hence, it returns a core constraint. In the classic case, this constraint is always a clause, as this is the type of constraint learned by current generation MAXSAT, answer set programming, and constraint programming systems. In our example, the returned core is the clause that says that one of x2, x3, or x4 must be true. This is implied by the formula, and it is clearly not consistent with the chosen assumptions. Based on this clausal core, we now reformulate the problem. For this, we determine C star, the smallest objective coefficient for a variable in the core. We now create an extension constraint by picking fresh variables, adding these to the core and making it an equality. The idea is that we add a sufficient amount of fresh variables so that any evaluation of the left-hand side of the extension constraint can be represented by the right-hand side. In our example, we know that the sum of x2, x3, and x4 will always be at least 1. That's what the core enforces. And at most 3. So adding 2 fresh variables is enough. As a result, the extension constraint does not cut away any solutions and can soundly be added to the formula, together with a simple symmetry breaker on the fresh variables. Now we reformulate the objective by subtracting the left-hand side of the extension constraint and adding its right-hand side, both multiplied by c star. The reformulated objective function lost the variable x2 and added y1 and y2, and it still only has both positive coefficients. Importantly, it also has the constant term 2, which corresponds to c star. In fact, c star is a lower bound to this reformulated objective function. Crucially, the reformulated objective is not fundamentally different from the original one. It is only rewritten with some new variables. As a result, its lower bound extends to the original objective as well. And that's it. We found a lower bound and are ready to call the solver again, with a new set of assumptions that assumes the lowest possible value for the reformulated objective. This was classical core-guided optimization. What changes when we use a cutting planes reasoning solver to generate cores? That's what our paper investigates. Initially, nothing changes. We call the solver with assumptions that assume a minimal value for the objective function. However, the returned core is now not a clause, but a more general linear inequality, a cutting plane. This core is more complex and may still contain non-assumption variables, or assumed variables with negative coefficients. These can be eliminated by adding Boolean axioms. Still, our core can have arbitrarily large coefficients, which make it hard to distill a lower bound from it. To remedy this, we reduce all the coefficients in the core to 1, for example, by dividing the largest coefficient and rounding up by dividing by the largest coefficient and rounding up all fractional values. As linear constraints with coefficients 1 are called cardinality constraints, we call the resulting core the cardinality core. With this cardinality core, we can now reformulate the problem. We again determine c star, the highest objective coefficient for a variable in the core. We also pinpoint the cardinality degree, which is the right-hand side of the cardinality core. We now create an extension constraint in a similar way as in the classic case, introducing just enough fresh variables to capture all satisfying assignments to the variables in the core. We extend the formula in exactly the same way, but in the example, we don't need a symmetry breaker as there is only one fresh variable. And finally, we reformulate the objective by subtracting the left-hand side and adding the right-hand side of the extension constraint multiplied by c star. Note that contrary to the clausal core case, the lower bound increase is not just c star, but the multiple of c star and the cardinality degree, for a total value of 4 in the example. After noting this lower bound increase, the core-guided loop continues as before. To summarize, the advantage of core-guided search in a cutting plane context versus clausal core-guided search is threefold. First, the core itself can be stronger, leading to, second, a stronger lower bound per core. Third, In a clausal context, the extension constraint is added to the solver by a potentially cumbersome re-encoding to a set of clauses, which is not needed in a cutting plane setting, as the solver supports linear inequalities. In the paper, we investigated also many different optimizations to cutting planes core-guided optimization. We summarized 3 of them here. The first one concerns the way we obtain the cardinality constraints. A single cutting plane score can imply multiple different cardinality cores. In the end, we settled on an approach that picked the implied cardinality core that will yield the best lower bound to the objective function. In our example, 2 cardinality cores are implied by the initial core. The C star of the second cardinality core is higher than the C star of the first, yet the final lower bound implied by the first is still better, so our approach would reduce to the first cardinality core in this example. The second optimization involves the way the extension constraint is encoded. Note that each auxiliary variable y represents whether the left-hand side of the extension constraint takes some value. In our example, y1 is true if and only if the left-hand side is at least 3, and y2 is true if and only if the left-hand side is at least 4. Instead of using the extension constraint as one big equality, we can split it along the auxiliary variables. In that case, we can start by introducing only the extension constraint for the smallest auxiliary variable, since as long as this variable is assumed false, all the other extension constraints are implied. This reduces the number of variables introduced by each subsequent reformulation. Optimization 3 is conceptually simple. Instead of employing only core-guided optimization, we alternate it with regular linear optimization, where no assumptions are made and the satisfying assignment leads to an upper bound constraint. Hence, we obtain an anytime algorithm where both upper and lower bounds to the objective function are constructed. The core motivation for this is the observation that core-guided optimization works really well on some problems, but not that well on others. Interleaving both in a time-sharing manner ensures at least half of the time the right optimization scheme is applied. To experimentally verify our approach, we implemented our core-guided technique in the pseudo-Boolean solver rounding sot, which uses advanced cutting planes reasoning. In this first plot, regular vanilla rounding sot is plotted, together with 2 other state-of-the-art pseudo-Boolean solvers, sat4j and naps. The plot is a CDF plot, with on the x-axis a timeout limit and on the y-axis the number of instances solved within this limit. Hence, the more to the top, the better performing a solver configuration is. The problem set is the optimization benchmark set of the most recent pseudo-Boolean competition. The best performing solver is naps, which is not surprising, as this solver also performed best in the actual competition. However, when we add the core-guided version of rounding sot to the mix, it outperforms all other approaches. Moreover, adding the interleaving version, which combines rounding sot's regular linear optimization with the core-guided optimization routine, we see another significant increase in the number of solved instances. This made us pretty happy, but there is a caveat to be made here. When we experimented with the MIP solver skip, which does not use core-guided optimization, we noticed that it handily beats all pseudo-Boolean solvers on this benchmark set, and it would have won the competition had it participated. Though our core-guided work reduces the gap between pseudo-Boolean solvers and MIP solvers, we were not able to fully close it. One reason is that skip employs advanced preprocessing techniques, which can greatly simplify a problem. Rounding SAT, on the other hand, has no preprocessor. A more targeted experiment investigates the advantage of a cardinality core compared to a clausal core. The solver configuration on the x-axis reduces the cutting plane score to a minimal length clause, while the approach on the y-axis reduces to the cardinality core yielding the best upper bound, as explained previously. Each data point represents an instance solved to optimality by both approaches, using only core-guided optimization, no linear optimization here. The coordinates of the point represent how many cores were constructed to reach optimality. We take a lower number to be better, as it represents fewer solver calls. It is clear from the plot that for most instances, the cardinality core generated as many or fewer cores than the clausal core, supporting the claim that cardinality cores are stronger. Finally, a similar picture is painted by our last plot, where we compare the number of auxiliary variables introduced before reaching optimality for the lazy extension encoding and the regular eager extension encoding. It turns out that for a significant number of instances, the lazy extension encoding introduced at least an order of magnitude fewer auxiliary variables. To summarize, the contribution of our work is the extension of core-guided optimization to a cutting planes reasoning context, and the investigation of different ways to optimize this process. This led to an approach that can more efficiently search for cores, can find stronger cores, does not require re-encoding of the extension constraint to clauses, and just makes a lot of optimizations easier and more natural. Doing so, we observe a significant performance improvement in rounding SAT, though there still is a performance gap with the MIP solver skip. Looking into skip's preprocessing techniques seems interesting future work in this regard.